Okay, good to have you on a Wednesday, August 18 on a Zoom meeting. And we have one more Zoom, which is tomorrow. It's a review if you want to join. And then Friday, there is no Zoom meetings. I'm going to post the exam, final exams on the same approach as exam number 1 and 2. So you're gonna start at 1 o'clock and you're gonna end at 3:40. Okay, 3:40. The questions will come from maybe because it's comprehensive. The number of chapters I've covered. I tried to pick one problem from each chapter, but there's more problem from chapter 15 and 16, possibly 17. Okay, let's see. So chapter 15 and 16 is a heat transfer by convection, conduction, and radiation. And then also the network, how to determine the thermal resistance for a plain wall or thermal resistance for composite wall. It's and combinations of the parallel walls, and also there's an air gap, there's insulation. So we're going to create a circuit or network, and then we can use that to determine the total or overall heat transfer coefficient. If you wanted to maybe down the road to go to graduate school, or if you wanted to major in, say, mechanical engineering, you will be exposed to solar design of solar energy, solar collector, and HVAC, heating, ventilation, and air conditioning. In that course, if somebody wants to open an air conditioning company, especially in Kuwait, you need that, right? You want to be in charge of an air conditioning company. So it's a good business, especially for hot climate. And if you could come up with a more efficient way to run the AC cooling, and then you don't need that much heating in that environment, right? But there will be sometimes you need to heat the space, or you need the hot water for the water heaters. That's another unit that you can add. Call it central air conditioning unit. Or nowadays they have a standalone unit, which for each room you'll have a unit that has, so you don't want it to put AC in the entire structure because it costs money. And nowadays the engineers are coming up with a better design than having a huge air conditioning unit in your backyard or outside of the house. So if many students, my former student, went into business of HVAC, heating, ventilation, air conditioning, because they had the business degree also and stuff, just continuing with engineering. After bachelor, they went and got the master's degree in business administration. And so those are the things that are recommended if someone wants to go to graduate school. After engineering, business will be a good, field to get into. Many people like to work in an area or environment of, trying to be a manager of a company. So you need some knowledge of business. Okay. So, and all right. So I just wanted to review. Those are in my younger days, I had many students that they came from different countries and took HVAC class with me at the SDSU. And we had fun designing the air conditioning unit for given blueprints or for residential and commercial buildings. And it took us a long time to calculate the overall heat transfer coefficient. Okay, so based on that, then you could come up with the tons of refrigeration, whether it's a 2 tons, 3 tons, 4 tons, they go by tons. They got a refrigeration cycle. but it's HVAC. That is a sensitive also, because if you recommend too high of a ton of refrigeration that is not needed, it is consider that to be a waste of money, and you've got a higher unit that was needed for that building. So you got the cooling and that environment so fast, and it was so uncomfortable. It was so uncomfortable. So you got to have a right size for the, it depends on the square feet of the house, or meter square or square feet. Okay. All right. Anyway, that reminds me of my, younger age that I was teaching at SDSU, and they needed, someone to teach an energy course. Also, that it was like 25 years ago. Okay, most of you were not born, or all of you were not born. Anyway, so you guys are great. It's good to have you in my class. It is pleasure always to see students that are really dedicated, wanted to learn. And I was so happy to look at your work. It was really a nice work. You did a good job, and a couple of mistakes here and there. So it's understandable. But if you really learn that, that was really a good work. And I could tell that this is, if you have learned the materials that I've covered, this is fantastic. That's a good feedback. All right, excellent. Okay, all right, so excellent work. And we've got one student that is not, or one or two that's not showing up to the Zoom meeting. Again, it's not mandatory to come to Zoom meetings, but if you don't take the test, then that goes against you. So I see maybe one student didn't take the test. All right, we'll be posting again exam number 2, grades and the solutions to the exam number 2, as BB or Sam requested, and it's I'm glad that you asked me that. So I put down a nice step-by-step work for you. But again, your work was almost 90-95%, maybe a few percent I deducted because of certain mistakes. Okay? So that's all I wanted to tell you. Any questions before I begin on just a little bit of chapter 15 and 16, and then go to chapter 17? Okay. All right. So I've already posted all the PowerPoints and all that. Maybe all the notes, I'm going to take pictures and then post it for you. Okay. So that is, I have all of them stacked together. So I could take pictures and then convert it to PDF and then post it on, say, I put a date. I think this time I just made it clear that the Zoom meeting recording was from, that's one, I think I made a mistake. I said it was on Monday that was, we had Zoom meeting, and Monday there was no Zoom meeting, it was Friday. All right. And then that, I couldn't directly upload the recording to Blackboard for chapter 15. That will, remember, I was reviewing chapter 12 and 14, and chapter 15 I covered a little bit. And you were right. I went and checked on Blackboard. I couldn't open it. So there was an error of uploading that recording for Friday, not Monday. So that was my mistake. I said Monday. There was no Zoom meeting on Monday. It was exam time. So what I did was I transferred it or uploaded to my YouTube account. So then I got the link of YouTube and I made it unlisted for other students. So then I posted the link. Okay, I think that's what I did. And it worked nicely. So then I had 2 more from yesterday, 2 more videos So there was total of, I think, 4 videos, maybe two from last Friday, and 2 from Tuesday. And then for today, if I was not able to directly upload, called videos, upload to Blackboard, it seems like the Blackboard has a limit of video size. If it's too big, it's not gonna let me upload it directly. So I can go indirectly and save it or upload it to YouTube, and then copy the link and paste it in that Blackboard folder, folder I call it. Okay, so let me just go back to my handwriting. Okay, all right, so let me see what I have. Okay. So let's see. In radiation heat transfer, okay. All right, so move this to the side and bring this a little bit closer. And that is fantastic. Okay, and that is a straight. So, and radiation heat transfer, we already talked about that, is the only heat process that does not require a medium to transfer energy from a hotter region to a cooler region. So like the sun is going to radiate heat to the surrounding, to the environment, which I like to have a cloudy day. I don't like the sun, so too much sun is going to damage your skin. So radiation of electromagnetic waves, or radiation consists of electromagnetic waves. And then we use the Stefan Boltzmann constant, the change in heat over the delta T. In this, I think in chapter 12 and 14, we use a volume flow rate, which is a V dot instead of Q, because Q, I mean, it's okay to say Q or Q dot, because it's used for energy or the heat transfer, okay, Q. So equals the per unit time is equivalent to emissivity times the Stefan Boltzmann constant times area times temperature to the 4th power. And the Stefan Boltzmann constant is given in the table, and area, surface area for the given problem, and emissivity is between 0 and 1. For radiation, emissivity for shiny surface is approximately 0. For black body is 1. All right, so this is, remember that if it is a black body in the problem statement, then in this formula here, emissivity is 1. So you're going to reduce this to this formula here. And if it's a heat flux, then you divide by area. So you have sigma only times T to the 4th, okay? Okay, so what is the rate at which energy leaves an object? What's the rate, okay? An object that radiate energy well also absorb energy well, and an object that radiate poorly also absorb poorly. Okay. So we have the materials, it depends on materials properties, and then you can look that up to see the convective heat transfer coefficient or the thermoconductivity of the materials. So anyway, these are all experimentally determined, okay? It's experimentally determined. That's good to know that. I think I enjoy teaching lab because it's a reality. So you can just hands-on activities instead of theory. So you can come up with the data that you're collecting during that process of experimentation. Like this coming semester, I'm teaching heat transfer. lab, upper division about MENG 400, and also fluid mechanics lab together in the entire semester. We have about 8 experiments, and we go over the fluid flow and heat exchangers, pump, and also for conduction heat transfer, convection heat transfer experiment, and also radiation. Okay? Radiation. So if you go here, an example. This is a person cools by radiation. A person cools by radiation. Suppose a person stands in a room with dark walls at a temperature of 18 degrees. If emissivity of the skin is 71%, 0.71, and the temperature of the skin is 36 degrees C, calculate the net radiation rate. Okay, we want to calculate the net radiation rate. So that is better here. All right. This formula here is going to be applied. Net rate of radiation. Calculate the net rate of radiation is this here, delta Q or delta T. So 0.71 Stefan Boltzmann. Area is given in the problem. That area will be 1.6 square meter. And then we got the temperature in degree, say 18, and degrees C, we add 273. Okay, so we have the temperature of the skin, 36 plus 273 absolute temperature. Otherwise, it's going to be wrong. Okay, to the fourth power minus 18 plus 270 to the fourth power. So the net radiation. So a person cools by radiation. Determine the net radiation rate is 124 joules per second. Okay. All right, so you got in a short period of time that we have, I think you have learned quite a bit. Okay, normally I spent 16 weeks trying to explain this heat transfer, but all right, so this is fast, but you know, you got the ideas, you have learned a lot, and that's important. All right, so and any radiator or black body emits. So again, if it's a B, means rate at which the energy is released. If it's a black body, you have only sigma times surface to the temperature of the surface of fourth power. And that is the absolute temperature of the surface in Kelvin. A real surface emits at this formula, the amount of energy emitted from the surface. Okay. An object may also absorb radiation. So G, which is the rate at which energy is absorbed. So G absorbed is alpha times G. Alpha, we said, is absorptivity. Epsilon means emissivity. Okay. So absorptivity. So the G is incident radiation. Okay, incident radiation minus the irradiation. Okay, some will be absorbed, some will be emitted or reflected to the atmosphere. So that's a capital letter G. Okay, and that is a last for this page, chapter 15. We have a surrounding at the temperature, we call it surrounding, an area of this surface here with a TS. All right, TS. So net rate of radiation from a surface, we have the net rate, Q equals E emission minus irradiation. So emission, energy, emission, epsilon times area times sigma times surface to the fourth power, and then minus the absorptivities times area, that's a irradiation, okay? Irradiation, and times sigma times temperature of the surrounding to the fourth power. So that's a nice formula to know. If emissivity and absorptivity is equal, we call it a gray surface, okay? A gray surface. In that situation, epsilon is equal to alpha, which is absorptivity. Or the, if you want to call this Q prime, maybe, rate of heat transfer, epsilon times area divided times sigma times the difference of the absolute temperature to the fourth power. So if it's a heat flux, okay, if it's a heat flux, because heat flux is the heat transfer rate per unit area, then we have epsilon times sigma times T S to the fourth minus T of surrounding to the fourth power. So, okay, so I think I'm giving you enough problems for chapter 15 and 16. That will be a good practice for you, okay? Review that. The exam questions will be similar to that, all right? And all right, so we go now to chapter 17, okay? Chapter 17, let's see, where do I have? Okay, there we go. All right, let's see what we have on chapter 17. Okay, chapter 17 is continuation of chapter 15 and 16, but now they're gonna include, because when the flow of air, whether it's a laminar flow or turbulent flow, going over a flat surface or cylindrical surface, or airfoil, there will be a boundary layer, thickness or boundary layer involved in that situation. And we know the convective heat transfer, free convection and forced convection heat transfer over a flat plate with certain length. So heat transfer by convection, thermal boundary layer we're going to be talking about, and the surface Q double prime means surface heat flux, which is equivalent to the heat flux by convection. So H subscript X, because this is the flat plate, we have as function of X. So by convection, we have the on the environment, we have T infinity, and then we have a velocity infinity, which the moving air, we call it the moving air, right? All right, so in that region. And so this is a beautiful formula. It's a per unit area, okay? Per unit area, H subscript X. And then we got to revisit the Reynolds numbers, okay? Reynolds number, which we call it a critical Reynolds number, okay? Reynolds number as a function of X, or for the leading edge, or this is X and this is Y. Okay, so RE, Reynolds number subscript X, comma C, critical. It's a velocity of the surrounding or the environment times the X, okay, X, that is the length of the plate, or you call it L, XC equals L. So critical length, and then little v means kinematic viscosity, and the critical Reynolds number corresponding to the onset of transition, critical. Like in the exam question, there was a boundary, we want to calculate the boundary layer thickness, and we calculated the Reynolds number, and we found out that the Reynolds number is in a transition region. When you have a Reynolds number that is considered to be between the laminar and turbulent, we call it transition region. Then you got to test the Reynolds boundary layer thickness that is designed for laminar flow, and the boundary layer thickness for turbulent flow. We just wanted to know what percentage of the flow is within the laminar region and what percent within the turbulent region. If most of the, the higher percentages will be in the laminar, then we say the laminar boundary layer thickness, therefore, is concluded that the boundary layer thickness is associated with laminar flow. That will be like a comparison. Okay, so Nussel, there's another number, okay? There is many other numbers in this chapter 17. So I just wanted to introduce you to two more numbers. We had the Reynolds number already. We're gonna have a Nussel number, NU subscript L, and Prandtl numbers, okay? Prandtl numbers, you can look that up as a function of temperature. You can look that up in a table in the back of your textbook or in appendices HT3, and you can get the Prandtl number, all right, for 20 degrees C or 100 degrees or whatever. Okay, so we're going to say PR, Prandtl number. So Nussel number, that's how it's pronounced, Nusselt or Nussel, okay? T, in America, the T is always, they just, they don't pronounce it. So Nussel, like often, they say often. They don't pronounce T. But British, they say often, okay? Often. But Americans say often, okay? Often. Nussel number represents the dimensionless temperature gradient at the surface. So Nussel number as a function of length, it's H, which is a convective transfer coefficient, times the length divided by thermal conductivity. So this is the famous formula. We call it the Nussel number, okay? Nussel number, very good. Okay, so this is another number. I just want you to be exposed to this, formulation, so that it's in the future, if you wanted to go to graduate school, at least you say, yeah, I've been exposed to this formulas, and I know that this is dimensionless, the same as Nussel number, the same as the Reynolds number. Okay, all right. So Prandtl number is a transport property. Is a transport property of the fluid for different gases, or for different, or for liquid, different liquid, water, for example, of the fluid. And okay, let me just go here a little bit. All right, so let's see to see that. Okay, great. And provides the Nussel number provides a measure of the relative effectiveness of momentum of an energy transport in the hydrodynamics and thermal boundary layers. So this number, Prandtl number, it can be defined by CP, which is a specific heat or capacity, heat capacity at constant pressure, dynamic viscosity over thermal conductivity. And also this can be written as a kinematic viscosity over thermal diffusivity. This is alpha now. In this chapter is not absorptivities. They call it the thermal diffusivities. So if you go to chapter 16 also, you have this formula in chapter 16, which is on page, I go to chapter 16, beginning of chapter 16, and it's, let me see if I, okay, it's equation 16.5 on page 361. It says the So if we look at the thermal diffusivities, which is a meter square per second, it measures the ability of the materials conduct energy relative to its ability to store energy. Materials with large alpha will respond more quickly to changes in their thermal environment, while materials with a small thermal diffusivity will respond more slowly, taking longer to reach a new equilibrium condition. So the product of rho C rho, this is not a CP, okay? So this is confusing a little bit here, but don't worry about this here. Just look at this ratio, and also it's given in the table. So look at that ratio, and alpha is actually the ratio of K over the product of the C and rho C, we call it, or C rho. Maybe I should just say rho C, okay? And volumetric heat capacity, this together, the product of the two parameters, rho and C, they call it volumetric heat capacity. And that is, again, you can look that up for Prandtl number in the appendices. All right, I have an example to go over, okay? Let me see what we have. We have one thing. So, all right, so let me just do this. And chapter 17, okay? So, okay. All right, so let's see what we have in here. Okay. Are you guys awake? I hope you are focusing on this. This is a nice problem. Okay, all right. So again, the table HT-3 is where you can go and find all the properties. Okay, and you can, like, Prandtl number for the function of temperature is this value, 0.687, approximately 0.7. Okay. So in this example, we have air. Okay, the fluid is air at atmospheric pressure and at a temperature of 300 degrees Celsius, flows steadily with a velocity of 10 meters per second over a flat plate. Okay, so we have a flat plate, and then we have a flow of air at a temperature of 300 degrees C, and the velocity, which we call it the environment, okay, or atmosphere, or air, outside air, is flowing at 10 meters per second. The surface temperature of this material, this flat plate, is 27 degrees C, and the length of the plate is 0.5. They didn't give us the width, okay? We don't know the width. So we're gonna say per unit width, okay? Per unit width. Okay, so if we look at one more time, so this amount of air with a velocity of 10 meters per second at a temperature of 300 degrees Celsius flows steadily with a velocity of 10 meters per second over a flat plate, or a flat plate of length 0.5 meters. The question, it says estimate or approximate the cooling rate per unit width of the plate needed to maintain a surface temperature of 27 degrees. Say you are designing certain, a unit, and that unit, they require the design temperature. It says it has to maintain 27 degrees C. Estimate the cooling rate per unit width of the plate needed to maintain this surface temperature at 27 degrees C. Okay, all right. You can go to this table and you can go to this table based on 300 degrees Celsius. you can find the kinematic viscosity, and then you have the thermal conductivity if you need that, or maybe let me see, do we need the thermal conductivity in here? We don't. Yeah, we need it. Okay, there is a need there. Okay, yeah. So Q prime means heat transfer rate. Okay, and then we're going to talk about H bar. Okay, I'm going to introduce you to the average heat transfer coefficient for conductive heat transfer times the length times T infinity minus T surface. Okay. All right. So this is the formula we're going to be using. Okay. Where it says estimate the cooling rate per unit width. Okay. That's a formula. Now the Reynolds number is the velocity times length divided by kinematic viscosity, which you are familiar with this now. You're an expert on this. So 10 meters per second, 0.5 meters. Kinematic viscosity is this number here from the table at 300 degrees C. So the Reynolds number came up to be 1.62 times 10 to the fifth. We know that the critical Reynolds number is 5 times 10 to the fifth square. Since the Reynolds number for this problem as a function of length, 0.5 meters, came out to be less than the critical, therefore we have the laminar flow. Please do not get confused between internal flow, Reynolds number calculation, and external flow. So over flat plate, external flow. So the Reynolds number, the laminar flow limit and transition and turbulent will be different. Okay, do not get confused between those two conditions, internal flow and external flow. Okay, so then we're going to calculate the Nusselt number. Okay, Nusselt number. So we have a formula in the textbook. The Nusselt number, you can go to one table here on chapter 17. Sorry about that. Let me just get this out of the way. Okay. Chapter 17. If you go to this table, it gives you the list of number. So if you go to page 423, it says the flow over flat plate for laminar and the turbulent, mixed, and so on. Do not worry about the mix. So we got the laminar, and the boundary layer thickness, a local Nusselt number as a function of x, and average Nusselt number. So this is the bar means average Nusselt number. This is given as an equation 17.26. Okay, 17.26. The derivation it's in the book, so no need to worry about the derivation. So for many years, I've been teaching this class. I said the Nusselt number for laminar flow is this guy here. Okay, this formula here. Okay, let me see if I can see it. Okay, all right. So we got 0.664 some factor times, let me just, okay, 0.664 times Reynolds number as a function of length, or x. Here the length is 0.5 meters to the power of 1/2, or the square root of Reynolds number, times the Prandtl number to the power of 1/3. Okay. So we already calculated the Reynolds number. Okay. So this is the Reynolds number. We're going to substitute in here. And as a matter of fact, some of you did a great job. Your handwriting was so nice. it was good to look at your work because it was so clean. But some others, it was difficult to read the handwriting. All right, just please read. It's good to have a good handwriting. Okay, I try to have a good handwriting, but it's not perfect. Okay, perfect. So anyway, um, so and then your printer number, you go to this table HT-3 and the appendices. Okay, so it gives the printer number. I'll just say approximately 0.7 or 0.687, but let's say 0.687. Sometimes you have to do interpolation because the temperature that you is given is not there. Okay, all right, so okay, so you plug it into here to the power monitor, and the Nusselt number, the average Nusselt number came out to be 236. It's a dimensionless. Okay, then the average convectivity transfer coefficient is the average of Nusselt number times thermal conductivity over length. So Nusselt number, we calculated 236 times the thermal conductivity. We got it from here, from the table. So 36.4 times 10 to the negative 3 watt per meter Kelvin. Or we can write it in decimal instead of scientific. That's a scientific notation when you have a 10 to the power, okay? Okay. So we got the thermal conductivity. We plug it into this here, 0.0364 or 36.4 times 10 to the negative third over 0.5 gives us the average heat transfer coefficient of 17.2 watt per meter squared. Okay. The average, so this we call it the average convection coefficient, average, the H bar. Okay, great. Now, the required cooling rate, per unit width of this flat plate is H bar L, T infinity minus Ts, and 17.2 we calculated for the average convection coefficient. Length is 0.5. The difference between the environmental temperature and the surface temperature would come up with 2,348 watt per meters, or you say 2.348 kilowatts per meter divided by 1,000. Okay, so that's the rate, required cooling rate, or 2.348 kilowatt per meters. Okay, kilowatt. Okay. All right. So really the overall or the bulk of the knowledge that I was expecting to share with you about the combination of conduction, thermodynamics, fluid mechanics, and heat transfer in a short period of time. Law of materials was just, you've been exposed to law of topics, but you have done a great job and do well on the final exam also. Just do the few, the homework problems. I try to maybe assign you to one or two problems, homework problem for chapter 17, just for you to be exposed to this language of Nusselt number, Prandtl number, and it's very, very straightforward. Okay, very straightforward. You know how to go to the table to find the properties, and always just write down where you got your information. Okay, just label, say which table. Okay, from table, for example, HT-3, and always write the formulas. Okay, this one thing I always explain in all my engineering classes.
such as statics, dynamics, materials, circuits. I teach circuits also, electric circuits. Um, I think I'm courageous to teach that because the mechanical engineers normally don't want to teach electric circuits class. Not at USD, okay, at other places, at the Mesa College. Yeah, I started at Mesa College about 37 years ago, and I have built a program, a very nice program preparation for engineers that they like to transfer to four-year institution. And if anybody wants to take computer aided design, CAD, and you want to learn about solid modeling, how to design things, parts, solid models, and mechanical drawing, we have a lot of openings and the school start on Mondays online. It's fully online. So, but I'm going to have a Zoom. I like to see my students or talk to my students. That I tell them come to the Zoom if you have any questions, so we can I can help you out with that. So if anybody is interested, there's a Messer College. You don't have to come to the campus because it's fully online for the CAD class. There's a one. There's a three sections. There's a one section that is it has a low enrollment considered for USD like 10 students. That's great, but having 12 students even better. So for Mesa College, they want minimum of 16 or 17 students for the course to continue. So just in case if you are in need of a unit that you need to graduate, you can always think about the Mesa College class. Okay, all right. So let me know if you email me if you need more information. So what else I wanted to share with you? That is all right. So okay, guys. I'm done with these three topics, and it's again, I will come up with I was talking about the formulas. Okay, sorry, I went to a different direction. Okay, it is very important to always write down the formula. I've seen that on the exam, students are just plugging the number without saying what this is. Correct? That is really bad because the student, somebody is really say, what is this for? Without even indicating that this is a formula here. Okay, so just for your own good, okay, make sure that you write the governing formulas, and those formulas are going to derive or take you to the next level. Say, okay, now I plug the number in this, and this is the unitless, no problem. This is unitless because it's a Reynolds number. And then we have average conductivity transfer coefficient. It has a unit of watt per meter squared Kelvin. And then, all right. Any questions? Let me just get out. Here, and now you can see me. We got Vivi here. I attended meetings for like a couple of hours this morning. They said you sign your name at the beginning, and then you sign your name in the middle of the presentation. And a chat room, you also sign when you leave the end of the presentation. So, but anyway, and they say you gotta have your face present. And I like to, but that's okay. I'm not gonna make it mandatory. VV is just thumbs up. Okay, all right, thank you. It says that because I know I've not seen you, most of you, except just I saw Abdul Rahman. I know how he looks like, and I don't know whether you guys are, Sam, Rashid, Zamzam. Zamzam has taken a couple of classes with me. Saleh Al Kadimi. I have no idea. So hope if you are on campus, you can find me on Tuesday and Thursday. at 9:15, I'm in the mechanics of materials lab or heat transfer lab in the first floor, where the computer uh, CAD class is, and then the next two doors down on the first floor. I will be in that room on Tuesdays and Thursdays from 9:15 to approximately, it depends on the lab. Students might finish the lab at 11 o'clock, but the class goes until 12. Okay, so wish you all the best. And I'm gonna stop recording. And again, the exam questions, okay? Similar to exam 1 and exam 2. Just a little bit from, thermal, problem from thermodynamics, problem from fluid mechanics, and problem from heat transfer. The reason I'm doing that, because we have accreditation, people are coming to evaluate the program, mechanical engineering, industrial, and electrical. So over summer and the last semester, because I'm the oldest faculty that I'm not a full-time, because I'm full-time somewhere else. So it's not a good idea to be full-time at two different places. So, but I'm fine with it. Okay, I've been there longer than anybody else. So it starts at the same class. Yeah. Same time. Would be also from 6 to 8 questions. Yes. From 6 to 8 questions. Yeah. Maybe 6 questions, maybe 7 questions. Okay, or maybe 5 questions. I need to have this, because the course is Introduction to Thermal Sciences, Thermal Fluid and Heat Transfer. So I need to assess your learning on those 3 topics, which we call it the final exams, okay? The last exam, comprehensive. Because they want me to provide, when I say that, because they don't ask any other part of faculty to do that. Because I've been there longer than anybody else, so they asked me to provide some samples, samples of the project, sample exams, sample that. Okay, so sometimes we just cross out the name. We just wanted to, the people that are visiting, they want to see whether, this course, it's called Thermal Sciences, what kind of problem is being proposed or given to you. That is something, it's part of the business, okay? I've been dealing with this for 30 some years, over 30 years now. But teaching part is easy. The business aspect of the teaching, dealing with the department, with the programs and all that. I spent like 7 consecutive years building the engineering program at Mesa from scratch. And then we got now the Berkeley people respect us, the Purdue University, UCLA, SDSU, of course, and USD. We send the students from Mesa College to USD, which we have done that for many years, and with Dr. Olson, Dr. Jacobitz, and we were, I invited them to come there to give a presentation so that we could recruit students to come to USD when we started the program mechanical. First, it was in electrical. I came to USD when I was teaching all the mechanical engineering classes to WE. Imagine statics and dynamics, 7:50 a.m. in a basement teaching mechanical engineering courses, 2 of them combined, static and dynamics, to electrical engineering students that most of them were asleep in the class. And I tried to wake them up. So that was tough, trying to, teach a course that I enjoy teaching, but they didn't want to listen. But anyway, it was a good time. So again, if you're planning to go to graduate school, think about if it's a USD, we don't have an engineering grad.
we're talking about that, maybe to bring a graduate program, and students can get a master's degree in engineering, okay, any field of engineering. But one day, we started in 1988 with electrical engineering, and then by 1990 something, 96, 7, 8, we started with it was industrial, then it was mechanical, then it's a general engineering. So we don't have civil engineering, we don't have aerospace, and also maybe some people wanted to major in construction, environmental engineering. We don't have that. It costs money to build a program. But there's a beautiful lab, and Dr. No and I, we're good friends, and then she's always doing something, project, and fantastic professor. We all work together, and we have known each other for many, many years. So, and you guys are maybe, I hope you had a good experience at USD, and many more people from students from Kuwait, from Saudi Arabia, from UAE, and from Qatar. I've not seen so many students from Qatar. So, and from everywhere. So we're trying to bring as many students possible to USD, and it's a very good campus for the school. And hope to see you on campus. And let me just stop recording.